let's get started. So again, like this is same things as probability. So this is supposed to be an prerequisite for machine learning course and the reinforcement learning course as well. So this is supposed to be a refresher on linear algebra, and I'll also be covering some of the Python parts to implement some of the things that you need for doing matrix related operations and vector related operations, and that will be useful for the machine learning and reinforcement learning courses. Let's get started. So before we start the tutorial, so what you need to know is that you should be already familiar with what the vector is, what the matrix is, and some basic vector operations and basic matrix operations like addition, multiplication, transpose, and for matrix you need to know how to multiply it with a scalar and another vector or a different matrix, right? So this is like very basic stuff, so we will not be covering any of those things in this tutorial. So in this tutorial we'll be covering a lot of other things which I think that are needed for both of these courses. Okay, so let's first start with scalars, vectors, and matrices. Okay, so let's see. So first of all, what basically is a vector? So we will be using something. Vector is basically like some sort of an arrow, right? So like this is pointing to somewhere, and this is what we'll be using as vector. And it is supposed to be in some sort of a vector space. So, and how exactly is this vector space defined? So, right, so we basically need some more vectors, right, to define a vector space. So like if we have some sort of a grid, right? So for example, like if this is my x-axis and this is my y-axis, then I know that I have a grid, and I can basically like represent this vector as in this kind of a grid line, right? So this is what we call as a vector space. Okay, so this is like in 2 dimensions, but vectors will have more than 1 dimension. But yeah, it's always easier to visualize things in 2 and 3 dimensions, right? So this is like my grid space, like grid lines, which we'll call it as a vector space, and we will use this for all understanding all of the things in our linear algebra part tutorial, right? So we can basically define the entire grid space with just 2 vectors. So one is a unit vector in x-axis and one is unit vector in y-axis. And by just adding or multiplying, adding and rotating these vectors, stretching and basically adding those vectors, we can basically generate any vector in this entire grid space, right? So I have only drawn the positive quadrant, but assume that these things are going in the negative quadrants as well, right? So if you stretch it enough, like till here, and then you stretch this vector till here, and then add these 2 vectors, then you get this vector, right? So it's very basic thing. So that's the basics of a vector space and a vector, and what basically so like again, like a vector space is basically defined with just bunch of vectors. They are called the basis, right? So in our case, it is I hat, which is unit vector in the x-axis direction, and j hat, right? So which is this one. So those are the basis for this case, which is often called the standard basis. And sometimes we can even use different sorts of bases to define a completely different grid, and then this vector will remain the same, but it will have a different representation. So in this case, like the representation of this vector might be like this is 3, and this is like what was it, something like 2.5. So this vector is something like 3 and 2.5, right? But if we have a completely different grid which is defined with a completely different basis, then we can have a completely different representation of the same vector. Okay, so with that we will cover it later, but that's like the basic part of the what vectors are and what the vector space is. And when we see when you talk about matrices, so you can always see the matrices as something that is transforming this entire vector space, right? Just transforming this grid. So what we are allowed to do is we can basically stretch out, like you can see this as a sheet or something, and we can basically stretch the entire sheet so that each and every grid line is equally stretched. and we can even rotate it, like, so to some extent, like we can make this this vector go over here, and this vector go over here, and this vector go over somewhere else, and like as long as every vector is following the same rule, that's kind of a valid kind of a transformation. So in other words, like when we talk about matrices, it is basically doing a transformation of this vector space, and those transformations are not all sorts of transformations. Those are basically the linear transformations, right? So basically every grid line is equally stretched or squeezed or rotated in as defined by the matrices. Okay, so that's what we will be seeing as the metrics, as what we call as metrics. And yeah, so so we know what basically a vector is, we know what basically a matrix is, and the tensors and other things are basically kind of a generalization of those things, right? So let's get into this cell and see what this is. So we already saw what a vector is, right, and what a vector space is, and we also saw like what like we can basically define entire vector space with just a bunch of vectors, which are called the basis vectors. So in like two-dimensional vector space, which is R2, we have standard bases as 0, 1, and 1, 0, right? So those are my standard bases, and matrices, as I said, is like the linear transformations of the vector space. So when you do any kind of linear transformation, we are allowed to do any kind of stretching and rotating and everything, as long as we keep the origin fixed. Okay, so everyone agrees that the origin should remain at its place. It cannot be moved to some other point. So as long as that requirement is satisfied, it's basically doing all matrices will be linear transformations, and every linear transformation can be represented by some or other matrix, right? So tensor is kind of an even more generalization, but we will not be covering this a lot in this tutorial. But tensors, like, so it's basically like you can see everything as a tensor, but say like scalar is basically order 0 tensor, scalar vector is order 1 tensor, matrix is order 2 tensors, and order 3 tensor, and you can go higher and higher in that line and in that direction. Okay, so you'll end up getting more tensors and other generalizations of it. So the Python part, now let's jump into it. So import functions are kind of very easy. So some of them I think you would have seen in the previous Python tutorial, but we will be probably revisiting some of those things in this tutorial as well, right? So if it is repeated, like, don't worry about it. Like, you get to learn things twice and things like that. Okay, so all we need is basically NumPy and NumPy linear algebra and a norm from the SciPy stats, right? So you don't really need to import the EIG part, but as long as you have the NumPy.linear algebra imported, that should be enough, right? So let's import those things. And how do we basically represent vectors is, okay, it is connecting, initializing. I should have done that before. Okay, so everything is imported. Now the way we define a vector is basically NumPy arrays, right? So vectors and matrices and everything that we will be using is simply just NumPy arrays. So you have learned NumPy in the previous tutorial, or if you haven't attended it, then somewhere else. Then like you can basically define a vector as a simple NumPy array. Here we have used the two-dimensional array just to show that it is a row vector, but you don't really need two-dimensional array for representing vectors in whenever you write code. So it's one-dimensional array should be enough. So as you can see, like, shape of this vector is 1, 3, and you can also define a column array where you can just basically take the transpose. Like, the transpose is like very easy, like just add dot t, and that will be your transpose, and this is how a column vector would look like, right? So you don't really need the second dimension here again, but like since we are just talking about vectors in 2 dimensions, we will represent it. This is not really a vector in 2 dimensions, but it's like a second order kind of a vector. So that's why we are basically representing 2-dimensional arrays. Okay, so that covers up the first part, which is scalars, basic introduction of scalars, vectors, and matrices. Now let's jump into standard matrix operations. So you already know how to do standard matrix operations on paper, but now I'll be covering some of this part, how to do these things in Python, right? So matrix again is basically a NumPy array. So I just defined a matrix and print it like it's all ones. But there is another way to define this kind of a matrix where we want all ones, which is basically use some NumPy's specific initializers. So we'll see that in this tutorial later on, right? So we will need one more vector. Let's call it vector B, matrix B. And now let's do a scalar multiplication, right? So scalar multiplication, as you all know, is basically multiplying every entry of the matrix with that scalar. And when we do the scalar multiplications, it's basically same as like just, writing down that constant number times the matrix. And that should do the trick, and that will do exactly the same thing as what we know as the scalar multiplication with a matrix, right? So that is easy. Matrix addition is also very trivial, like just add those two numbers like you are adding two variables, and that will do the matrix addition part. Matrix transpose is even easier, just write .t and that will be your transpose, right? So this is like very trivial, easy things to do in NumPy and Python. And finally, the matrix multiplication. So we have this kind of thing where we like basically, this is how we do matrix multiplications, and you already know this part. And how do we do this kind of a multiplication in Python is, you can't really do just matrix A times matrix B like you did the addition. You need to do this, you need to use this dot function. So you just do numpy dot and then pass on the two matrices, and that will do the matrix multiplication, right? So sometimes you know that for matrix multiplication, certain shape requirements are necessary. So the second dimension of the matrix should be the first dimension of the second matrix that we are trying to multiply. And if that is not happening, then we will get an error, right? So for example, if we have a matrix with shapes 3 by 2 and 3 by 2, then we cannot really do a dot product of those two matrices, right? So if we try to do the dot product, then we will hit an exception and your code will crash. Okay, so this is not crashing because it is in try and except kind of a block. So, but if you don't put things in try and except kind of a block, then your code will be crashing and you will be hitting issues. Okay. Matrix vector multiplication is again like pretty much same as matrix multiplication. If you know matrix, then you also should know matrix vector multiplication, right? So it's exactly the same function that I'm using. It's the same dot function, and if you do it, then you get the matrix times vector. So this is the matrix A, and this is like vector B that I've defined here, and we do the dot product and we see the result like this, right? So you already know how to compute the shape of the result. So it is like 4 by 3 and 3 by 1. That's what we are multiplying. In that case, the result will be 4 by 1, right? So that's the matrix operations. And now let's see how to define some specific types of matrices. So like if you want to initialize sometimes a matrix, you can always initialize things with random entries, and this is how you do it. You just call numpy.random.rand and then specify the shape of your matrix that you want to initialize, and it will basically create a matrix with this shape 3 by 2 with random numbers in it. Okay, and if you every time I execute this cell, it will be different entries. If you want to reproduce some results and everything, then you need to fix the seed, and once you fix the seed, then you will always get the same numbers, right? So even though it is calling the random, but since the seed is fixed, then you will always get the same numbers. Okay, now yeah, you can always store matrices in a variable and do types of things on that variable directly. Okay, so this is kind of a very easy kind of stuff that we have seen before. So that ends this matrix operation part. And now let's jump on to, let's actually even skip the practice part, because the practice parts are kind of easy, and I have given you enough problems in your assignment 0, so you would be practicing things anyways, right? So if we have time left, then we will come back and revisit the practice part later on. So now let's talk about the rank of a matrix. Okay, so as I said earlier, okay, so we have seen matrices as a transformation of our space, right? So let's say basically we have we have a vector over here, and let's say we have some grid lines also. Let's draw some grid lines also with a different color maybe, right? So this is my x-axis, this is, okay, like my y-axis. And when I do some sort of matrix multiplication with this vector, then what I'm doing, matrix multiplication, then basically what I'm doing is transforming this vector space into some other vector space, right? So I'm basically stretching out this axis or this axis or rotating this axis or something. So let's say that after my matrix transformation, this vector will basically not land here. So let's say after my matrix transformation, my new grid lines are something like this, right? So I have transformed my x-axis to this line and my y-axis to this line, or rather, like, an easy way to define matrix transformation is just see how it transforms the I hat and j hat vectors. So that will basically give you the grid lines of the new vector space that is being transformed into, right? So this vector will also land somewhere else, right? So we don't know exactly where it will land. So we basically, if we multiply this vector with the matrix, then we will know, we will get another vector, and that will be, let's say, this is not the right exact answer, but let's say, like, in the new vector space, this blue vector comes over here, right? It may not have the same length, and it may not land on the similar distances from the axes and everything. So it depends on how my matrix has transformed the entire vector space, right? So this is a vector that is transformed into this vector, and every vector in this vector space will be transformed into some more other vector, right? And that will define another vector space. Now, what can happen, what I can do is I can do something more, right? So I can basically say things like that. I want to move my x-axis to this line, but I don't want to move my y-axis here. So let's erase some parts and let's redraw things. Okay, so let's say I have my x-axis, let's say I have my y-axis, right? And after the transformation, I want my x-axis to go here, and I want to completely collapse my y-axis, right? So in that case, what will happen is that, or let's even take a simpler example. Okay, so let's say I'm not really even transforming my x-axis, I'm just stretching it a little bit. So this is my new I hat vector. So this, if let's say this was my previous I hat vector, then this is my new unit vector in the x-axis, and the y-axis, I just completely collapsed it. I squeezed it so much so that now it is just basically a 1 point. In that case, what will happen to, say, particular vector, which was, so if this was the vector which was in the original vector space, then what will happen to it after the transformation is that it will basically stretch 2 times in the x-axis dimension, right? So this is where it will be stretched, and then y-axis will be simply collapsed, right, to 0. So it will land over here, right? So that's what happened to basically this vector, right? And let's say if I have another vector, right? Say basically, let's draw another vector, right? Okay, something like this, right? It has basically the same x-axis but different y-axis. Then it will also basically land. It will be stretched, like x-axis part will be stretched by 2, and then y-axis part will be collapsed to 0, and then it will land here. So you can see that I have a transformation, but it is not really doing a lot of things, right? So it is basically transforming entire vector space into a single line. So now the dimension of the new vector space is no longer 2. It is now 1. Right. So earlier it was 2-dimensional vectors. Now everything is landing on in this single line. Right. So that's what we can do with matrix transformations, and some more things we can do. Right. So you can even do like, let's not even transform the x-axis to something else. Let's squeeze x-axis also to 0. In that case, my x-axis and y-axis will be squeezed. Both of them will be squeezed to 0, and so every vector will land on the point 0, 0. Right. So that's what basically I'll be doing with if I have a completely, what do you call it, zero matrix. Right. So if I have this kind of a matrix where everything is 0, right? So this is, if you multiply it with any vector, then it will transform it into 0, and basically all the vectors are now coming over here all the way to the origin, right? So this is like collapsing the entire vector space into a 0-dimensional space, right? So this is how we will define the rank of a matrix. So where basically the rank of a matrix is something which is the resulting vector space, its dimension. So that resulting vector space's dimension is we will refer to as the rank of the matrix. You can also see it as how many independent, linearly independent rows or columns that matrix has. Okay, so that's basically the rank of a matrix, right? So if we have a matrix, right, so which is of rank 1, then it basically says that it transforms all the vectors on a line. So it basically transforms every vector, takes any vector in my original vector space and transforms it onto a line. And if we have a rank 2, then it will transform everything into a plane, right? So we have been discussing 2-dimensional vector spaces, but if we have, say, 3 or n-dimensional vector spaces and everything is transformed to a plane, then my matrix has the rank of rank 2, right? And similarly rank n and so on and so forth, right? So for example, in 2-dimensional vector space, if we consider this kind of a matrix where x-axis, like I hat vector has been transformed to vector 2 and 4, and j hat vector has been transformed to vector 3 and 6. In that case, all of my vectors, let's actually even try to see how this looks like, right? So I have my I hat, which is transformed to let's draw a smaller I hat, right? Because so smaller I hat, and this is 2, 3, 4, and let's see here also 2, 3, and okay, I am not drawing straight lines anymore. This is roughly straight line, so it will be good enough for us. Okay, so I hat is transformed to 2 and 4. So this is 2, and let's say here it is 4. It is going somewhere here. This I vector will be landing over here, and j hat is going to 3 and 6. So it is 3, and somewhere over here is 6, and it's basically like exactly the same line where these two vectors are going. So basically every vector will be squeezed onto this single line, and that's why this matrix has a rank 1, right? So this is a standard matrix which has a rank 2 because everything will be landing on something else. But as I said, some vectors can even have rank 0, which is basically all 0 vectors. Okay, so that was the rank of a matrix. It will become important when we try to solve equations using matrices, right? So that's like our next topic. So how do we solve equations using matrix? Is sometimes like we have this kind of an equation. So when we say that we are trying to solve an equation, so what exactly we are trying to solve is, so I have some vector x in my original vector space, and I want to find what is the vector that will be transformed to vector b after my after the transformation that is applied by matrix A, right? So matrix A is basically doing some transformation of the linear space. And now instead of trying to find out where my given vector will land, I want to find out which is the vector which will land on a particular vector if I multiply it by this matrix A, right? So that's what we are trying to solve. And now it will become easier to see that why it becomes necessary for this matrix A to have a full rank, or rather like higher rank. It should not be singular matrix. So the rank 0 or lower rank matrices are basically, like, we will call them as singular matrices. But yeah, so what will happen if I have a singular matrices? So if my matrix is transforming every vector into a line, then I will have multiple solutions, right? So for example, we saw earlier that we had a vector which was landing on 2, 0, and we had a different vector which was also landing on 2, 0 when we multiplied it with a vector, with a matrix with rank 1, right? So it might not be easier to find an answer, like unique answer, when we have matrices of lower rank, right? So that's why, like, when we try to find this kind of an answer, it becomes necessary that we have the matrix of full rank. So how do we solve this equation? It's basically when your matrix has the full rank, that means you can find an inverse transformation of that matrix also. So something, you transformed your vector space into some other vector space, and that next vector space, the other vector space has exactly the same dimension as the original vector space, then you can also find an inverse transformation that will transform your new vector space into your original vector space, right? So that's basically the inverse of the matrix, and sometimes the inverse will not be possible when the matrix has lower rank, right? So we basically multiply things with an inverse, and that's how you find the solution of the linear equation, right? So how do we do this in code? It's very simple. We define a matrix, we define a vector, and all we need to do is basically multiply this inverse of the matrix with the vector, and that's what we'll do. We will first compute the inverse of the matrix. So there is a simple formula to compute inverse of the matrix. It's numpy.linearalgebra.inverse, right? So once you have that, it will basically, numpy will do the job and it will compute the inverse for you. So some students were complaining about one of the question in the assignment 0. It's basically 2 lines of code. So yeah, you should basically be happy, or it's a very easy question. Like if you have to find an inverse of a matrix, just define the matrix and use this 1 line and you will find the inverse. Okay, so this was the matrix. It was 2, 3, 3, 2, and we compute the inverse. It will be this values, and once we have the inverse, technically you also know how to compute matrices on inverse of the matrix in paper, but we really don't need to know all of those things. We just need to know one Python function, and that should be enough. Right, so the unknown values is basically the dot product of the inverse with the vector, and that's how you get it, right? So you can actually even do the verification that my x should be 1 and 2, and how do we verify it? If you multiply matrix A with x, then it will land on the vector B. Somebody has any question? I guess you all are not muted. Okay, this is going in the recording, so good luck. Fine, so we did the verification, and it is landing on 8, 7, which was our original vector B. That's how we know that what we have computed is correct. Sometimes you need to do the verification because NumPy will have some numerical issues and everything. So most of the time you will not face numerical issues, but sometimes you will. So if you don't get the desired result, that's because of the numerical issues. Okay, so you can also solve it with in a different manner. So like we did like all the computation, we computed the inverse and then multiplied the inverse with a vector and all those things. But you can also do a single line of code instead of doing all those things. Just do numpy.linearalgebra.solve, and it will do all those necessary operations. It will take the inverse of this matrix A and multiply it with a vector B, and it will directly straight away give you the answer X, right? So you can also verify this part, and it is matching, right? So this is how you will do things in NumPy. Okay, so that is basic parts of solving equations. And when you cannot find the inverse, it's basically the determinant is 0 or A is singular, right? So if you have a matrix which does not have a full rank, then it will have, then basically we will call it a singular matrix. And as we saw earlier, why it is not possible to solve equations when you have transformations which is not really a full rank matrix, right? So Okay, it says that the computational complexity of finding A inverse is order of n cube, but it is actually less than n cube. We have better algorithms, but it is still higher than order of n square, right? So it is n raised to 2.7 or 2.4 or something like that. But it is an expensive operation. So if you have a very large matrix, then it will take some time to find the inverse. Okay, so you should keep that in mind. Okay, that was solving equation using matrix. And now let's talk about change of basis, right? So change of basis is kind of what we have been doing till now with the matrix operation, right? So, okay. So what is change of basis? So like, let's say I started with my I hat here and j hat here, and I had a vector, which is this vector, right? So in this vector, I know that what will be the coordinates of this vector in this metric space, right? So in this, if I use I hat and j hat as my basis, then I know the coordinates might be, let's say, what is it? This is 1, this is like 2, this is 3, and this is like 4, and this is what, 1, 2, and 3. So this might be like 4, 3, or something like that, right? So it is, let's even write it. Vector 4, 3, if I use I hat and j hat as my basis, but it might have a different coordinate if I use a completely different basis, right? So let's say if I use a completely different basis, let's try to actually write something easier this time, not make things complicated, right? So let's say my new basis is, instead of ij, I'll say I is basically x-axis is stretched to 2 and y-axis is, I don't know, stretched to 3. In that case, in this new coordinate system, right, this vector will have a different coordinates, right? It will have coordinates of 2, 1, right? So it's still the same vector, but it's now a different basis. And the different basis does not even need to like land on x-axis and y-axis, right? So my different basis can be something completely different. Like I can use this vector and this vector also as my basis, right? So this is also like, if you just stretch and add those two vectors, then you will be able to cover every vector in this vector space also. But I don't know what are the coordinates of this vector in this kind of metric space, right? So it's this kind of a vector space. So how do we find the coordinates of this? So first of all, why it is actually even important. So sometimes it might be easier to do operations on a different metric space, right? So for example, we'll actually see the examples later, but sometimes we want to do certain operations on a vector, and it might be easier to consider a different grid lines, which will make those operations easier to compute, right? So that's like the main idea why we want to sometimes do the change of basis. So how do we compute the change of basis? It's very simple, right? So what we are trying to find out is that what is the vector in the new coordinate system. So let's say I'm trying, so I have in R2, I have 1, 0 and 0, 1 as my basis vectors. And I have a vector which is given by 4, 5, right? So this is how normally I would represent 4, 5 in my original coordinate system, which is 4 times the first basis vector, and 5 times the second basis vector. So if I have a completely different basis, which is like, let's say 2, 1 and -1, 0, which are linearly independent, so they are like a valid basis, then what would be the coordinates of this vector 4, 5? So it's basically I multiplied 2, 1 by the coordinate A and -1, 0 by coordinate B, and it will give me this coordinate 4, 5, that same vector, right? So how do all I want to do is I just want to find out this coordinates A and B, and you can see that this is equivalent to doing a matrix multiplication of, put this 2, 1 on the x-axis, right? So it is basically like my new coordinate system is obtained by transforming my original coordinate system with this kind of a matrix, where x is going to 2, 1 and y is going to -1, 0. And I want to see which vector will land. So like basically I want to find out the representation of this 4, 5 vector in my new coordinate system, right? So it's basically saying as find which vector will land on my 4, 5. Oh, okay, it's kind of, this is kind of confusing. So what we are trying to find out, let's get this point. Okay, so we have this vector, and this was original 4, 5 in my original vector space, and we have a different basis, which is this and this, let's say. Then I want to find out what is the new representation of this vector, right? The grid lines might be, so one grid line is parallel to this, and the other grid line is parallel to this. So something like this. So these are like my new coordinates of this vector. That's what we are trying to find out, right? So that's this is like the equation type of a representation of this same problem that we are trying to find. And you have a question? Sorry, I couldn't hear you properly. Okay. So no questions.
No, sorry, it's my fault. Sorry.
Okay. So carry on. Like this is basically also it's equivalent to solving the linear equation, right? So how we solve the linear equation is that we just took the inverse of this matrix, and that's how we compute the unknown values, right? So this is basically exactly doing the same part, and we are trying to compute the unknown values, right? So we were basically trying to compute what would be the vector in my new space, which after the transformation will land on 4, 5 in the original space, right? So that's basically what we have computed, and which basically gives us the answer, which is 5 and 6, and you can actually even verify these answers, right? So to sum it up, basically all you have to do is, if you are transforming something from standard basis to a different non-standard basis, which is something like this, then how you will do that, like the shortcut method, like the overall crux of it, summary is that you represent that non-standard basis as a matrix, take the inverse and multiply the vector that you are trying to find the new representation of with its inverse, right? So that's how you basically find the new representation of your vector if you use a different basis. So that's how you compute the change of basis. I think there is a question about that in your assignment 0 for that. So that was change of basis. The next is the eigenvalues and eigenvectors. Okay, so how do we understand this eigenvalues and eigenvectors? Okay, let's actually do this. So let's consider this matrix, right? So it is transforming x-axis to -3 and -2. So let's actually try to even draw that. Okay. So I have my x-axis, I have my y-axis, right? So this is I hat and j hat. So I hat is transformed to -3, -2. So that will be 1, 2, 3, and -2 will be somewhere over here. So my I hat will be transformed to, let's use a different color, to -3, -2, and my y j hat remains the same, right? So this is still my j hat. So what happens to this matrix 1, 1? So 1, 1 is originally in my original vector space. It was over here, right? And after the transformation, where it will land. So after, if I do the transformation, it will basically do -2, -2, right? So it will, in my red metric space, I should have used green color, but it's okay. It will be this value, right? So it is -2, -2 over here. So this vector, right? So when I did the transformation, so this matrix is doing a lot of different transformation. It might be transforming, let's say, this vector to some other vector, which we don't know, let's say, so over here or somewhere, and things like that. But like this particular vector, it's a very, very special type of a vector, right? It didn't get rotated at all. It only got stretched, right? So it still remains on the same line. It just got stretched like in the opposite direction and by length 2. So that's like a special vector. It still remains on the same line even after the transformation, and those vectors are what we will call as eigenvectors, right? So they're kind of an important type of vectors because it represents some sort of some features of the transformation, right? So that's what we have. That's what this is basically saying, is that I transform this vector v with this matrix A, and all I get is the same vector, but which is not really transformed to a different vector. It's just stretched. So lambda is a scalar over here, right? So this lambda scalar, by amount in which I have which I have stretched that vector, is called the eigenvalue of that eigenvector, right? So how do we compute the eigenvectors? It's very simple. So of course, like, so eigenvectors are not just unique, like, so they're not unique. So there are a lot of vectors. In fact, like any vector which is in this line, like x equal to y, will only get stretched and it will not get rotated by this transformation. So that's there are like infinitely many eigenvectors, and for every eigenvector we have unique eigenvalue, right? So how do we, like, if we want to find out what are the eigenvalues? Okay, so eigenvalues will always be the constant, right? So it will not change. It will always be, those vectors will always be stretched by that fixed number, which is associated eigenvalue. So it's not a different eigenvalue for every eigenvector. It's the same eigenvalue for the same eigenvectors which are on the same lines, right? So how do we find those eigenvalues? It's basically like using those matrix equations. What we were doing is we were trying to solve this equation. And when we try to solve this equation, it is equivalent to putting this on the left-hand side and multiply this lambda with I. And when we solve this, this will give us the answer, right? So how, when this will have real solutions, is we have seen this before. This is a linear equation, and for this linear equation to have solutions, this matrix needs to be linearly independent. This matrix need to be of full rank, or rather, in other words, it should have zero determinant, right? Because the right hand side is 0 over here. So for this to have multiple, so like we need, so this needs to be not of full rank. It needs to have a kernel space, which is like a set of vector will land onto the same vector 0. That's what we are trying to find, which are those vectors. And for to have that, we need to have a determinant of this part should be 0, right? So this part a minus lambda I should be 0. And when you solve this, you will find something called a characteristic polynomial, which will give you the values of this lambda. And once you have the values of this lambda, then you can find out the eigenvectors, right? So that's how you basically do things on paper. When you have to do things on code, it is so much easier to do things, right? So it is, all we have to do is just define a matrix A, and instead of I'm dealing with matrix A, I'm actually dealing with a covariance matrix, because it is nicer in this particular case. And how do we compute the eigenvectors or eigenvalues? It's just this EIG function, which is in numpy.linear algebra. So if you recall earlier, that's we actually imported here this EIG function from numpy.linear algebra, right? So you use that function, and that function will compute the eigenvectors and eigenvalues for you, right? So this computes. These are basically my eigenvectors, Like it will give you two outputs. One is eigenvalues and other is eigenvectors, and you can print them. And these are your eigenvalues and these are your eigenvectors. So be very careful about that. So there are sometimes numerical issues in this. So for example, in this particular situations, right? So here for that particular matrix, the third eigenvalue is like e raised to minus 17, which is, you might know that it is by theory, if you compute it by hand, you might obtain 0, but it is not really showing you 0. It is showing some numbers, which is some sort of numerical issues happening in the calculations, right? So be careful when you compute eigenvalues and eigenvectors like this. Okay, so you can actually even verify this kind of things. Okay, why it is not working? Okay. So this was like a particular eigenvector, which is this one. And if you want to verify that A times this eigenvector is lambda times this eigenvector. So the left hand side is this matrix, and you can actually do the dot directly like this also, like matrix time dot, and that will also give you the vector. And the right hand side is this kind of thing, like, so it is eigenvalues of 0, which is a scalar, times that vector. It will also give you exactly the same answer, right? So that's how we find the eigenvectors and eigenvalues, and it will become useful later on. So when we talk about something called diagonalization, so what exactly is a diagonalization? So we sometimes want to write this kind of a matrix A as we want to transform it into some vector. D is something which you call a diagonal matrix, where like you have only the diagonal entries there. So for example, like so if you have like 3 by 3, then you have this entry, these entries are non-zero, and every other entries are 0. Right, so all of these cross entries are 0, and you only have this dot entries. So why, like sometimes like this kind of representation, like if we want to find some matrix P and D, so that like first we transform it using P, then we transform it using diagonal matrix tree, and then we transform it using the inverse of the P, then all these three transformation sequence of this transformation is equivalent to transforming this matrix A, right? So why do we want to do this kind of stuff? So like, let's imagine like if we manage to find this kind of P and D, then let's say if I want to find A to the power 3, right? So how do we do this? Is that I will do PD P inverse, that's 1. Second is PD P inverse, that's 2. And the third one is again like PD P inverse, that's 3, right? And you see that all these parts, intermediate parts, are getting cancelled out. So all of this is equivalent to doing P and then taking the cube of this diagonal matrix and doing this inverse transformation again. And we all know that like it should be very trivial to understand that, you know, taking the higher powers of a diagonal matrix is so much easier, right? You only have to multiply each value of each corresponding value with its corresponding value, and like basically take the cubes of each diagonal entries, and then you are done, right? So a lot of this kind of operations becomes easier when you can diagonalize a matrix, and not every matrix can be diagonalized, because that's what something that you'll have to answer this kind of questions on your assignment 0. So how do we diagonalize a matrix? So it's again by using, one of the method is by using eigenvectors and eigenvalues. So what do? Is you find the eigenvectors and eigenvalues, and you put all your eigenvalues in this matrix S. Where is it? Yeah, this S matrix, and the corresponding eigenvalues, right? Are basically lambda 1, lambda 2. They are also in a matrix which is called lambda, but they are basically like the diagonal entries of this lambda matrix. So if you multiply this A times S, so A times the first eigenvalue is basically same as lambda 1 times the first eigenvalue. A times the second eigenvalue is lambda 2 times second eigenvalue, and so on and so forth. So this is, when you do this A times matrix S, is basically doing S times this lambda, right? So when you do this kind of things, then it's very easy to notice over here that if you multiply by S inverse on the right hand side, then you get A as S lambda S inverse, and S is your desired P. Lambda is the diagonal matrix which is made of eigenvalues, and the S inverse is like your P inverse, right? So that's how you do the diagonalization using eigenvectors and eigenvalues. Now we will jump on to the slightly less important stuff, which is norms. So norms is basically a way to measure the magnitudes, right? So when we talk about vectors, we want to find the magnitude of that vector. And there are lots of ways to find the magnitude of that vector. We can just simply measure its length. It's like one magnitude. And the other way of measuring the magnitude is something called norm1 of that vector. It's basically you sum all the coordinates that you are using in your grid lines, and when you sum up all those coordinates, then you get another number which is also in some ways magnitude of that vector, right? So that's there are basically like, and you can basically define norms in many different ways. Like your norm is basically a function which takes your vector as an input and will output a real number as an output. But that functions cannot be anything like that. Those functions need to basically satisfy a bunch of properties. Like, for example, norms of a zero vector should always be zero, and things like that. Norms of like two same vectors should be the same, and things like that. A lot of different properties. We don't really care about those things. So what we will be discussing here is like the P norm, which is you take every coordinate, take the pth power, take the summation, and then take the pth root of that matrix, right? So that's when P equal to 1, it's basically the L1 norm. When P equal to 2, it's L2 norm, which is basically measuring the length of the vector, which you can also calculate it as simply by doing that vector transpose that vector, right? So this will also give you a single number. And when you have to compute this kind of things with Python code, then this is how you do it. You define a vector. How do you find the norms is you have NumPy linear algebra, and from linear algebra, you have this function called norm. And once you pass the norm, then it will compute the norm of a vector, and you need to specify which norm that you want to compute. By default, it will compute the L2 norm, where like P equal to 2 here. It's just like the most common, the length of that vector. But if you want to compute a different norm, which is like 1 or infinity or something, then you have to pass it as a second argument, and it will compute that particular norm, right? So it is 4 and 3. Just add up these absolute values, that is 7. And the L2 norm will be 5, 4, right? So it's very easy to see. So that was norms. Trace operator is kind of a trivial thing, like just sum of all the diagonal entries is your trace. How do you do it? Just matrix.trace. That's it in Python. Right? So trace of the matrix, just do matrix.trace, and it will do the trace. It will compute the trace for you. Right. So that computes the trace operator. I think we left out the practice example, but the practice examples are very simple. So one of them, I'm just asking you to verify this property that the matrix multiplication is associative, right? So how do you verify it? It's basically you define 3. This is not a full proof method to do it, verify things. Like it's one way to verify things. It's not a completely valid proof. All I'm doing is I'm computing a random matrix ABC, 3 random matrices, and then on one side I'm doing this BC first and then doing the dot product with A, and the other side I'm doing AB first and then doing the dot product with C, right? So when you do that, we compare the outputs. It is exactly the same outputs, and that's why the matrix multiplication is associative. You can do some more practice if you want of matrix multiplication and using this kind of Python code. If you want to do it, I'll just ask you to verify there's another property that this is basically this matrix multiplication is basically distributive, right? So if you do A plus B times C, it should be exactly same as AC plus BC, right? So that I'll not execute, like you do it on your own. So that brings us to the end of this tutorial. So by the way, for eigenvectors and eigenvalues, if you want to learn more, I have given a link of this 3 blue 1 brown channel, which is like a very good tutorial on eigenvectors and eigenvalues. And if you want more tutorials, then there are more links. Like there is one PDF from Stanford, and there is one more PDF from MIT. So this should be enough to understand all the things in your machine learning course. And I think it should be enough to even answer all your questions in your assignment 0. Do you have any questions? So we have one question related to assignment 0, which I don't need to answer right now. I'll just answer it after I finish the recording. Any other questions? Is there any other question? Okay, so I'm going to stop the sharing part, and I'm also going to stop the recording, and now I'll answer. Okay, somebody wants me to re-explain diagonalization. Okay, we can do that. We can do that, definitely. Let's share the screen again. Okay, so diagonalization. Okay, so which part do you need help with? Like the diagonalization of how I did the diagonalization, or how why the diagonalization is important? Olivier. How I did it. Okay, so what I did was I computed the eigenvectors and eigenvalues of this matrix, right? So if you remember, the property of eigenvectors is this, like when V is the eigenvector and lambda is my eigenvalue, then it will satisfy this property. When I multiply this A matrix with vector V, I will get my eigenvalue times the same vector V, right? So this part is the property of the eigenvectors and eigenvalues. So what I'm doing is that I computed the eigenvectors of this matrix A, and I just put it in my in a matrix, right? So let's say I have my first eigenvector, so I put it here. Second eigenvector, I put it here. Third eigenvector, I put it here, and so on and so forth, right? So I have a bunch of eigenvectors, and I just put them here. So I call this as my matrix S. So this is my one eigenvector, this is my second eigenvector, and this is my third eigenvector. All right. So I have this matrix S, and what will happen if I do this kind of a multiplication, A times S? So when I do this A times S, it's basically same as multiplying A with each of these columns, right? So it is exactly same as A times the first column of S, A times the second column of S, A times the third column of S, and so on and so forth. So what is A times the first column of S? It is basically A times this eigenvector, which is also same as lambda times that eigenvector, because that's the property of eigenvectors. Similarly, A times this second eigenvector is lambda times this eigenvector, second eigenvector. A times third and nth eigenvector is lambda times this third eigenvector. So it's corresponding lambdas and S, right? So and what I did is I computed another matrix which is called capital lambda, right? So it is a diagonal matrix where I have lambda 1 here, lambda 2 here, and so on, lambda n here, right? So it is, so what I'm doing here is basically same as S times lambda. So S times lambda 1, right? So this is the same thing like this. So lambda is scalar, so you can put it on the right hand side also. It's exactly same as S1 times lambda 1, right? So this is S times lambda 2. This is S times lambda 3, and so on and so forth, right? So this is, okay, this is not AS, so this is S. So S times lambda is basically this matrix. So I just say that AS is same as lambda S. So when I have this equation, all I have to do is just multiply with S inverse on both the side, and I get this thing on the right hand side, which is SAS inverse, which is what I wanted, which is PD P inverse. So that's how I did the diagonalization. So my P matrix is my S matrix, my D is my capital lambda, and P inverse is basically inverse of this S matrix. Is that clear? Yeah, okay. Any other question? You didn't get Julian's question. What was Julian's question? Yeah, so I haven't answered it. So that was related to assignment 0. So I'm going to first stop the recording and then I'll answer that question. So if there are no other questions, I'm going to stop the recording. And then let's answer the question for assignment 0.